Hi, and welcome back to another episode of Artiste. This is an unusual episode because some of you may wonder, after watching the content, why did you call it Artiste? Well, there is art, there is the art, there is the artist, there's the artistry, and there is the fundamentals of the music that allows us to use all these expressions. So, in a few episodes, we are now going to discuss what is within the music, specifically what we call Indian classical music. What goes inside the movements? Can we imagine those movements and learn from those movements? And maybe machines can help us. Or is it too modern? Is it too scientific for us to even think in this manner? Just do your riyaz, your sadhana, and sing and enjoy. That's one view. But there is also an entire world of imagination that opens up the moment you study the secrets behind what we feel. And that's what we're going to try and do in the next few episodes. And we're going to be talking to four individuals, and I'm going to call them music scientists. Not words that you use together, but I'm going to call them that. I'm going to first introduce them before I call them onto the screen. I wish we could do this directly, but the COVID restrictions and difficulties has made this an online conversation. With me today is Ajay Srinivasamurthy, who was part of this very important comp music project, which was led by Professor Javier Serra from Spain, and worked on several automatic rhythm analysis problems in Indian art music. His current research interests and experience include speech, audio and music signal processing, and machine learning. He continues to collaborate on different projects, building tools for computational musicology. Computational musicology, that's a new word, Ajay. I've not heard that before. So welcome, Ajay. That's our first participant.
Thank you.
Next, pleasure. Nice to have you. The next person is Kaustuv Kanti Ganguli. He is a student of Hindustani vocal music, having learned from Pandit Ajay Chakraborty. He is an engineering graduate from IIT Bombay. He's also been associated with the Comp Music Project ever since its inception and has postdoctoral experience at the Music and Sound Cultures Research Lab at NYU Abu Dhabi. In fact, he's joining us today from Abu Dhabi. And Kaustuv envisions to converge his musical and technological skills to research on cognitively based artificial intelligence for Indian art music. I'm sure, Kaustuv, there are going to be a lot of people who are uncomfortable with that phrasing. Artificial intelligence for Indian art music? Well, explain that to us. Kaustuv, welcome to the conversation.
Namaskaram. Very glad and honored to be part of this. Looking forward.
Thank you. Next is Ranjani. Ranjani has obtained her master's and PhD degree from Indian Institute of Science, Bangalore. Her PhD thesis focused on computational approaches for melodic analysis of Indian music. She has also the experience of working in the industry on embedded systems and signal processing domains. That word you're going to hear a lot today, signal processing. So register it right now. Her research interests include signal processing, machine learning applied to speech, audio, music, and communication. Ranjani, welcome aboard.
Thanks. Happy to be here.
Thank you. Then we have a fourth participant, Vignesh Ishwar, well-known Carnatic musician. He's a BE in electrical engineering and did his research at IIT Madras under the guidance of Professor Hema Murthy. Hema Murthy led the Carnatic music research part of the Comp Music Project. Following that, he also did his master's in sound and music computing at the Music Technology Group, UPF Barcelona, and focused on the Comp Music Project led by Javier Serra. And Javier Serra is the big brain as far as signal processing and understanding goes across the world. So we're going to be probably referring a lot to him today. He's not present. I wish Javier will join us at some point of time. And he has worked on, Vignesh has worked on several problems which are related to melodic analysis with regard specifically to Carnatic music. So I am the only non-scientist in this entire gathering. and therefore going to be asking you probably very silly questions, basic questions. And I would ask the scientists here to bear with my limited knowledge and explain to me what is going on. What did you do? Or what are you doing? And how can this, shall we say, change our understanding, maybe even practice of music? To the audience, we are going to be focusing specifically on two forms of music, correct me if I'm wrong, which is Carnatic music and Hindustani music specifically. And those are the areas where all the four scientists have worked a lot. Okay, so let me start with the absolutely fundamental question. What is signal processing? Unmute yourself, all of you, and any one of you can take it up. What is signal processing? Explain this to me. I'm only a musician.
Right. Well, I can start, and then probably other people can pitch in if something needs to be added. So
That's sure.
Signal processing is essentially an engineering discipline right now, which deals with processing signals. And when we say signal, it's any form of information that like humans and machines can produce. So say, for example, when we speak, speech is a signal, and when we sing, music is again another signal. And then they are recorded in multiple forms when we record them on a microphone, for example, or the signals could also be recorded, for example, from an antenna, or for that matter, even other devices that we use for collecting information. And once we have that information, their signal processing is just, for me, a set of tools that help us to analyze the content of what's there in those signals. And then so that's basic, so very basic signal processing for me. And then given the complexity of each of these signals and the information that's contained in them, so that the tools can be as sophisticated or as easy as if we could use them for.
Okay, I'm just going to ask Kaustuv a question, just move from here. Okay, you have signals, you have different kinds of signals, he himself talked about. Is there anything unique about the audio signal? Because we are going to be discussing specifically sound as a signal. Is there anything unique about sound as a signal that you receive?
Definitely. So talking in engineering terms, we call is kind of pseudo-stationary signals, because it's different from a randomly generated signal. So music as a sound has some stationary points. So it is stable over a period of time, which we can kind of think as invariant within that time frame. And we have a very basic assumptions to do signal processing based on those time frames that we call window. So we window the signal and then extract some features of it. For example, if we talk specifically about music signal, it can be a predominant melody. So if you are producing the voice and it has a pitch, then we can extract the pitch from the audio signal, assuming that it is stationary over a short period of time. So
sorry, can you explain
the
meaning of the word stationary? Are you saying there is a predictability in the signal? What do you mean by saying the signal is stationary or the audio signal is stationary?
So for the formal definition, I'll not go into like engineering definition of stationary, but it is kind of stable within a tolerance for a given amount of time.
Okay.
So it's also very much dependent on perception. So many of these methods are derived from the perception and the production, the way we produce music. For example, there is a just noticeable difference. So if you just make so it's not musical because it is not stable on a pitch with a tolerance for a reasonable amount of time.
So there is that means the tolerance is a set is a determinant based on perception, the level of tolerance.
Yes, it is. Yes.
Okay, that's interesting. So would that mean that tolerance changes from the kind of music that we are dealing with?
Yes.
Very much so, and also based on this like center frequency. So the tolerance will be different from a lower octave to a higher octave for natural singing. So, and we embed all this information in the signal processing chain.
Okay. Well, thank you very much. So I'm just going to go to the next word, and before we come back to music again, is machine learning, and I'd like Ranjani to respond. So, I mean, we've all heard this word, machine learning, but can you explain? What does it mean when we say machine learns? What do we mean?
Okay. So I'll put it this way. Okay. Others can add on. Signal processing is capable of actually obtaining certain low-level information from the signal as such, but it cannot generalize across all of it. So you want to go into a higher level of information. So let's say signal processing is able to give you the pitch, but can it give you the tonic information? May not be. It is not yet there. So that is when, or can we look at the raga directly from the signal processing? May not be. So you want to generalize across things. You want to look at patterns which are repetitive. You want to go slightly higher up from the perception on towards the cognition, but there are many levels there. And that is where we bring in machine learning. And what happens with machine learning is you're teaching the machine so as to learn certain tasks, so as to be able to automate it and scale it across different data. That it's quite powerful in terms of being able to generalize across certain tasks, and that is what we call as machine learning. But nowadays there's a lot of blur between what is called as signal processing and machine learning. It's very, very hazy. There's no boundary there. So yeah, we call it SPML, and yeah.
But they both need to coexist in some manner, right? You can't have one without the other. So in a way, you can't just have signal processing happening unless there's machine learning and there is, if I may use a very layman term, a back-end work done with what information has been gathered, simple information or basic information that has been gathered, right?
Right.
Yes.
So, these days, yeah, go ahead.
Yeah, go ahead. Okay, I would put it this way. So depending on the information, if you want to, as I told, move away from perception on towards cognition, you will have some amount of machine learning there. Signal processing probably stands alone depending on the task, because it depends on where you are actually sampling for the task. That's how I would put it. Yeah, Ajay, you wanted to say something, please go ahead.
Yeah, I mean, this is something very similar to what you said. So, I mean, so the analogy, if we want to kind of look at how humans perceive and understand things, so signal processing, as you said, Krishna, is the front end, and then machine learning is the back end. So machine learning happens in our heads. Signal processing happens from our ears all the way till the brain.
So if I was going to use another analogy, I'll say one is hearing, the other is listening.
Yes.
Right? Because we all hear, but whether we all listen is a totally different question altogether.
Sure.
So I guess.
If I may chime in, just a small analogy. So in machine learning, we always go by learn through examples. So it's more of a target-oriented learning. So in signal processing, we have to feed the machine that, okay, this is the signal, then fundamental frequency is a feature of the signal, and you do it this way. But for machine learning, we give the target model. So this is the target. And from this example, you kind of reverse engineer to get all the features that is relevant to reach that target.
Right.
Got it.
Right.
Got it. Lovely.
Sorry,
go ahead. Vignesh, go ahead.
There is also the thing, I mean, as far as I understand it also, signal processing also gives you the information that machine learning helps you learn.
Correct.
You extract the information that you want to learn through signal processing, and you apply machine learning to learn it. And later on, the applications are pretty wide.
Right.
Yeah, and I also think that when you use machine learning and learn, your next experiment also tells you what information you want to again gather through signal processing. So kind of a cyclical kind of relationship, I guess, is built in it also. So I have a question for Vignesh, coming straight to say music and signal processing. Can you give us first some amount of background on how this, especially with Hindustani and Carnatic music, how did this relationship or this science kind of evolve? Some basic idea. And what do you do? Very simply asked. So you can start and somebody can take over from you too, of course.
Yes, of course. So actually, I'd like Ajay to talk about the history of how music signal processing came about and like what are the works that have been done before, and I can take up from there.
Sure. Ajay?
Right. So, well, signal processing itself is about 50, 60 years old now. And then signal processing for music is actually a much later thing that came about. It actually started mostly in military when they actually wanted to detect objects in the sky using radar, for example. And then it slowly evolved into signals that are produced by human beings. And then so signal processing for music itself started mostly to support music production. So for recording, for example, or storing them, or kind of building devices that could help, like recording, like synthesizers, for example, or and then so that's where it started. And then about 20 years ago or so, we started moving towards signal processing for analysis, wherein we already take up audio recordings which have been recorded, and then we now want to extract meaningful information out of them. And then that's, well, basically, if you look at some kind of history, so it started with production, then now it's analysis. Now it's also, there is a lot of impetus on, well, synthesis, and then actually not really synthesis, but also generation.
So Vignesh, can you explain this connection between Indian art music and signal processing?
Indian art music has a very definite pedagogy, and it has definite principles that we can actually look at and try and analyze. And when you look at the audio signal, you can, using these musical principles, it is very, it gives a lot of scope to extract information from the audio signal using these musical principles. That's how you try, and that's how I think the connection between music and signal processing came about, especially Indian art music and signal processing, because there are definite concepts such as raga, such as tala, which define melody and rhythm in various aspects. You have, so when you look at melody, you have shruti, you have raga. Shruti is tonic, and you have raga, which is melody and or melodic identity. Then you have tala, which can which can be divided into certain number of parts. Like, for example, the tala is the rhythmic cycle, or the tala can be the syllables of the rhythmic instruments that is being played, which can be recognized, and through that you can again get to the rhythmic cycle. So these kind of definite principles exist in Indian art music. Or, for example, I mean, from the comp music project, we saw that any art music tradition has certain principles like this, which we can exploit to apply signal processing principles and machine learning principles to gather information and then do analysis later on.
So can you tell me, for example, what kind of information were you gathering? How did it start? And if you can also share about your learnings through that, that'll be wonderful for us to understand what really you did.
So when I started out at IIT Madras doing my research for the comp music project, the first problem we tackled at that point in time was tonic recognition. The macro problem that any signal processing, music signal processing, the biggest problem for any music signal processing person is raga recognition, and getting like a really big, a really nice accuracy in that. So everything that we do finally leads to raga recognition, even though that may not be that important task for a musician or an artist.
Yeah, so let me just interrupt there and try to explain. When he says raga recognition, he's talking about the machine understanding and recognizing ragas, not human beings. Just to clarify that, so people understand we're talking about machines. Go ahead. Yeah.
Right, sorry, I was getting to that. So I mean, even though it may not be a very important problem for artists or musicians, for a machine per se, it's a very, very important problem. And everything that we have done we have always tried to use it in certain ways to get to that raga recognition problem. At IIT Madras, we started by recognizing tonic, because
is that so difficult to do? I'm just asking.
Yes. So tonic recognition is not that easy a task as humans recognize tonic for a machine, right? So and the very basic task for raga recognition is to first recognize the tonic, because without the tonic, a raga cannot be perceived.
Yes.
In context. So so we first got into tonic recognition, and we had recordings that we could work from. Now there are different sources of tonic, of shruti. There is the tambura that's playing in the recording. There is the singer that is singing. There is the mridangam that is playing. There is the violin. But we want one frequency. That one frequency has to be extracted. There are various sources to extract this one frequency. So it's not that only that one frequency is being played. There are so many other gamakas, and there is so much of music happening. There is rhythmic sound happening, there is melodic sound happening, there is the instrument violin sound happening, the vocal sound happening, the tambura sound happening.
There's too much information.
There's too much information. To sieve that information and get the tonic out of it is a challenging signal processing task.
Right. Very well summarized, actually. Yeah.
Ajay.
So I mean, so if we kind of take the other route, right? So if you kind of technically describe, so when we record music, right? So it encodes all the aspects of what we kind of perceive in music, and then it's very easy for like seasoned listeners to separate them out. Like as Vignesh was saying, melody and rhythm and timbre. Like these are the three dimensions, I would say. So it's very easy for us to kind of focus on.
I'm just going to pause you there and try. Can you give the listener, the viewer, on an idea of what timbre is, because that's not a word that is often heard in public.
Right. So well, the timbre. Well, the textbook definition is it's just the quality of a particular sound. But then the easiest way to understand it is by kind of saying what is it that is actually distinguishing the same note that's played on the veena versus the violin.
Exactly. Yeah.
That's timbre. And then, I mean, from a signal processing perspective, it's the content. So any signal, we typically decompose them into two aspects. One is on time, the other one is on frequency.
So Ajay, sorry, I'm pausing here. So something else you need to explain is about timbre. It's very important that we also realize that the signal that you will get will be different even if the same tone is played or note is played on a violin vis-a-vis a veena.
Yes. Very different.
So I think it's not just an experiential difference that happens as an audience, but the information is different is something to be important for people to realize, I think. I think that's where timbre plays such an important role as an expression.
Actually, I'd like to say something on that. Violin, if it's played, when the violin plays on the mid octave, as we hear it, it's actually the higher octave, according to the timbre of the violin, when compared to the human voice.
Yeah, exactly. Yeah.
Just for the timbre difference, how it plays a major role in deciding the sound.
And because of our listening, we normalize it, so we don't even know it's a different octave. So anyway, go ahead.
So just these statements, right? How do we formalize these things? So when we say this mid octave, we perceive it to be the same as say a particular different octave when we are singing. How do we formalize this definition in the signal, right? So that those are the problems that like signal processing tasks try to estimate. And as I said, like there are two main dimensions. This is also like we sing in time and then we sing in pitch as well. So these variations are captured in the signal. And then the way these variations show up in the signal are defines what is the timbre, pitch, and time. And we need to decompose this. And once we decompose it, we can actually try and focus on each of these dimensions and then extract useful information. And as Kaustuv said, we have to make a lot of assumptions when we are dealing with this in terms of like stationarity, as he said, which essentially means sound is remaining the same over a very short period of time. And then it's the same over a very short period of infrequency and things like that.
Ranjani, you had something to add, I think. Ranjani?
I was just wanting to tell that just like how you said that we normalize internally the tonic frequency, that is exactly the reason why we should be normalizing even for a machine, so that it knows it is supposed to normalize it. And there are many other things that we normalize.
Very important. So in a way, what you're telling me is that you in machine learning, or when you shall we say teach the machine to learn, if I can use that expression,
yes,
you are in a way asking the machine to behave like we would behave in the way that we perceive, right? Is that accurate?
Absolutely.
Exactly, concurring with your thoughts. So our perception is top down. We start from conceptual things to a phenomenon. But for signal processing or machine learning, it's bottom up. So we get to the low level features and then construct to the phenomenon. Correct. So a kind of good amalgamation where this is supplementary and complementary is the best and stable system. So that's why tonic identification is also a kind of challenging problem to start with, which is not so much in the human perception way, because it is doing exactly the opposite thing from constructing from the bottom up.
Okay, when you want the machine to learn, you're actually constructing bottom up, is what you're saying.
Yes.
Whereas we've already conceptually bought into the idea, and therefore, figuring out the exact frequency is coming from the other side.
Yes.
Exactly.
Right?
Exactly.
Interesting.
Right.
Very interesting.
And I just want to say that this window that we are talking about is in like milliseconds.
Yeah.
Yeah. So I have a question about your data now, because even Vignesh spoke about we are still at tonic. I know we've not been proceeded beyond tonic, but nevertheless, but in the question of the data that you use. So even for say tonic recognition, let's not even go beyond that, understanding a raga, etc., or even rhythm or rhythmscape. What kind of limitations do you put onto the data that you're trying to use for such an investigation?
Right. So the limitation actually is not from the signal processing perspective, but it's mostly from the application perspective. So it's mostly task driven. So if I want to kind of extract tonic from a particular signal, what is it that we should have in the signal so that we can actually recognize it. And then, I mean, of course, so that is completely, as I said at the beginning. So the tools that we will use will kind of can work better or worse depending on what information is already present in the signal. As I said, I mean, Kaustuv did a very good example there. So as we start from the concept of tonic, saying that now I want to sing in, say, I'm not sure, say for one particular tonic, and then that gets manifested in your audio signal. And then now we are starting with the audio signal without even the information of what exactly went in the conceptual space of the musician. So now we are trying to extract it back. And that's when we, in addition to what's there in the audio signal, we try to bring in a lot more human knowledge and then try to solve the problem of tonic estimation. And that's the information that Vignesh was talking about. Like right. Tonic can be extracted from the multiple instruments that are present in the recording. Correct. Or from the whole idea that every person in that recording is singing in the same tonic. These are all additional information that we bring in so that the tonic estimation problem becomes easier.
Got it. So I'm just going to... Yeah, go ahead, Kaustuv. Go ahead.
No, before we leave this context, I just wanted to give a kind of disclaimer. Why do we choose these problems to start with, even tonic identification, raga recognition? Because this is very easy to evaluate as a classification problem, because we can annotate by human experts or musicians, this is the tonic or this is the raga. And for machine learning models or signal processing models, these target models are very important to evaluate. So that's why our end goal is not to identify how good the machine estimates tonic or raga, but it's kind of a proof of concept that this is going in the right direction. For example, there can also be tonic identification correctly done if the raga information is given, because we know the intervals of the raga notes. Okay. And if we estimate the tonic wrongly, for example, the pancham is found as the tonic because that's also a very dominant note.
Correct.
But from the raga information...
Yeah, the system can think it is far. You're right. Yeah.
Yeah, but from the, if we have a supplementary information of the raga, then we can kind of self-correct the tonic. So it's kind of a feedback loop that we can use. So it all depends what is our final aim. Is it to estimate the tonic or is it to estimate the raga? And
so I mean, it's also important that you're creating a certain stability within the within what you're trying to find. And it's a question of how you're going to determine that stability. You could determine that stability from this end, or you determine that stability from what I would call raga content.
Right.
So raga content can tell you the stability is in the tonic, or the tonic can tell you that because it's the tonic, that is the raga content that you can probably perceive.
Correct.
You can work on both. Am I getting what you said, right? Just
and one more thing. Totally. One more thing is that there was also some work done in that we recognized the syllables of the mridangam and then determine tonic from that, because we know some of the syllables are played in the mridangam actually contain the tonic information.
Tonic itself. Okay. That's interesting. So now that he's introduced mridangam, I mean, it's good to talk about not just mridangam, could be tabla, could be pathavas, could be anything. But what about the audio signals in terms of rhythm, in terms of time, in terms of measure? How does that play out? What just like tonic is a fundamental information that you're looking for in melody in Indian art music, what is the fundamental start point for Indian art music rhythm?
Right. It's so it would be some kind of periodicity in time. So which would be like, I mean, what it's very popularly described in West music as pulse. Okay. So detecting that fundamental pulse, which will actually define all the structures of a thala, that would be the fundamental problem. And then the same kind of complexity exists there. I mean, so tonic estimation, the main complexities are, as Kaustuv mentioned, it could be the panchama detected as the tonic, or probably the next higher octave shadja. It's same thing here. Instead of I saying the pulse is 500 milliseconds, I say it is 250 milliseconds. It's still perceivable exactly. So it's wrong to call it octave, because octave has this implication of 8 notes, but then it's like doubling and halving or 1/3, any of these fractions of time.
Okay. So I'm going to pause here. We have barely scratched the surface, but I think we've got some basic idea of the connection between signal processing, machine learning, and simple things as tonic or shruti, as we call it, shruti and laya, tala. So I'm going to pause here and end this episode, but stay with us. This is going to be a long conversation, and we're going to dig deep into the science and the art of Indian art music. Thank you.